Hello, good morning students. I am Dr. Sunita Tandon from RR College Alwar. Today I am going to deliver a lecture on low temperature oxidation of methane. This lecture is from special paper of physical chemistry chemical dynamics. In the last lecture, we have studied about the normal reaction, normal oxidation of methane by oxygen. That was a simple oxidation reaction, and in that case, we have studied that the net reaction mechanism for methane oxidation is that one molecule of methane consumes dead 1.5 molecule of oxygen to form carbon monoxide and 2 water molecules, and this reaction is exothermic with a energy of 543.8 kilojoules per mole. It means oxidation of methane is exothermic reaction. Ordinarily, oxidation when takes place of CH4, it consumes 1.5 molecules of oxygen, and the net result is carbon monoxide and water molecules. Now we will study the low temperature oxidation of methane. The mechanism for low temperature combustion of methane different from the general mechanism because reaction with high activation lose their significance at low temperatures of the initiation reaction. When we are going to oxidize methane at low temperatures, that is normal course, then in such case, because the reaction has very high activation energy, then at that time the normal oxidation or low temperature oxidation loses their significance because low temperature of the initiation reaction, तो इनिशिएशन रिएक्शन का प्रॉपरली नहीं हो पाता. दैट्स वाई हम आज पढ़ रहे हैं ऑक्सीडेशन ऑफ मीथेन at low temperature. The collision mechanism initiation as given by equation 2 is of 1 and 2 magnitude. आप अभी देखेंगे, आगे हम इक्वेशंस लिखेंगे तब हम देखेंगे कि जो फर्स्ट हमने मीथेन का ऑक्सीडेशन रिएक्शन पढ़ा, देखिए आप ज़रा पीछे अपने नोट्स के अंदर पीडीएफ के अंदर देखिए कि हमने फर्स्ट और सेकंड ऑक्सीडेशन का जो तरीका पढ़ा मीथेन के ऑक्सीडेशन का, उसमें इक्वेशन 1 और 2 में क्या है, CH4 मॉलिक्यूल एब्जॉर्ब्स ऑक्सीजन एंड फॉर्म CH3 फ्री रेडिकल एंड HO2. दिस इज ठीक है, हाइड्रोजन एब्स्ट्रक्शन रिएक्शन दिस इज नोन एज फ्रॉम मीथेन बाय ऑक्सीजन. ठीक है, अ कोलिजन इंड्यूस्ड डिसोसिएशन ऑफ मीथेन ऑल्सो टेक प्लेस एंड इट react in that case CH4 reacts with M, a third body collision, and it forms CH3 radical and M. In these two reactions, the collision induced initiation as given by equation 2 is at 2 order of magnitude faster than 1 at 600 K. This is oxidation. CH4 with third body M is of the order of twice the magnitude faster than the reaction 1 of reaction 1 क्या है, CH4 with oxygen. Initiation reaction is accelerated by radicals that enhance the rate of oxidation of methane, considering the rate determining step in the collision induced dissociation at methane. Next है the most significant among these reactions are CH4 react with oxygen atom and form CH3 free radical, and hydrogen is abstracted and OH is formed. In the next reaction, this OH formed combines with CH4 again forms a CH3 radical and water molecule. The principal reaction that involve CH3 free radicals are CH3 free radical formed in the first two reactions. In these two reactions, then CH3 free radical combined with oxygen to form CH3O plus O, and then this O form react with CH3 free radical to form CH2O plus H. The methoxy radical react primarily, methoxy react is CH3O. It reacts primarily by the equation CH3O reacts with M to form CH2O plus H plus M, providing the major fraction of CH2O at low temperature. The decomposition at CH2O is given by CH2 collide with M to form HCO, H and M. Because it becomes significant. This reaction becomes significant because at high activation, the most significant reaction of CH2 at low temperature is CH2O plus O form HCO plus OH. This is the significant reaction at low temperature, and CH2O collide with M to form HCO, H and M. This is the significant reaction in case of normal reaction, which has energy of activation approximately 18 kilojoules per mole. This is followed by the production of carbon monoxide as given below. HCO formed in the above reaction, just above reaction, combines with O to form CO plus OH, which occurs at low temperature. The reaction which is responsible for production of carbon dioxide is given as CO combines with OH to form CO2 plus H, which has low energy of activation, that is 33 kilojoules per mole. For the reaction of carbon monoxide with hydrogen peroxy radical compared 96 kilojoules per mole. दो तरह के रिएक्शंस की एनर्जी को कंपेयर किया है. नाउ कार्बन मोनोऑक्साइड react with HO2 and form CO2 plus OH. Consequently, the reaction at CO with OH is most significant source of carbon dioxide in the combustion of methane. The terminating at the process given the termination of the process given by following radical reactions. HCO combines with H to form CO plus H2. HCO plus OH combines to form CO plus H2O. During the induction period, as observed in the reaction at low temperature, the nature of plot below changes in pressure delta P and time is given by. On y-axis we have taken delta P pressure change, and on the x-axis we have taken K, and the temperature is constant. At 480 degree we get a curve 1. When at the 500 we get a curve above 480. Then third is at 320 it is above, and at 340 is above. It means the most significant reaction for this induction period are given as follows. This time lapse between 0 axis on time and time, this is known as induction period. The most significant reaction for this induction periods are given as follows. CH4 combines with M with a rate constant of K1 to form CH3, H and M, and this is reaction number 1. Next reaction, in the next reaction, H react with oxygen with a rate constant of K2 to form OH plus oxygen, reaction number 2. CH4 combines with oxygen, rate constant K3 to form CH3 plus OH, reaction number 3. OH reacts with CH4 with rate constant K4, gives CH3 plus water, reaction number 4. CH3 plus O2 combines with rate constant K5 to form CH3O plus O. CH3O plus M reacts with rate constant K6 to form CH2 plus H plus M, reaction number 6. Similarly, CH3O reacts with oxygen atom with rate constant of K7 and forms CH2 plus H, reaction number 7. The concentration of CH4, oxygen and OH are constant during induction period. The species CH3O, HO, OH and CH3 are produced in a low concentration. The steady state approximation applied here. One thing I want to clear, that induction period is the period before the start of actual reaction, during which reacting molecule acquires that much of energy to perform a reaction. There is a lapse between actual reaction starting and the time from where we are going to start. We are studying it from zero time, and sometimes it takes 15 seconds to start the reaction. This time period is known as activation period or induced period. Now the steady state approximation applied. Thus d by dt of CH3O, it is given by, just imagine the CH3O जो है वो कहाँ कहाँ बन रहा है. जस्ट देखिए CH3 बन रहा है CH5 फिफ्थ रिएक्शन के अंदर, सिक्स में डिकम्पोज हो रहा है, तो 5 और 6 में CH3O काम में आ रहा है. तो हम रेट ऑफ डी बाई डी टी ऑफ CH3O पर स्टेडी स्टेट कंसेप्ट लगाएंगे, तो हमारी इक्वेशन होगी K5 इंटू कंसनट्रेशन ऑफ CH3 प्लस ऑक्सीजन, बिकॉज दीज आर द कंसनट्रेशन वेयर द CH3O इज फॉर्मिंग, and rate of according to steady state concept, rate of formation is equal to rate of its removal, and it is removed in equation number 6. So we can write d by dt of CH3O is equal to K5 CH3O O2 concentration minus Cx into concentration of CH3O and M, or this is equal to 0. It is also equal to 0. In such case K5 CH3O2 is equal to K6 CH3OM. Similarly, d by dt of H, d by dt of oxygen atom, d by dt of OH and d by dt of CH3 are determined as follows. First we take d by dt of H. H आप देखिए कि H कहाँ पर कंज्यूम हो रहा है और कहाँ बन रहा है. K1 रिएक्शन आपका पीछे है, उसमें CH4M से कोलाइड कर K1 रेट इक्वेशन से CH3H और M बना रहा है. इसलिए फर्स्ट स्टेप में H बन रहा है, तो रेट होगी इसकी स्टेडी स्टेट कंसेप्ट अप्लाई करने पर K1 CH4 concentration into concentration of M. In the second reaction, H is removed. This is equal to minus K2 into concentration of H into concentration of O2 plus K6. In sixth reaction it is also formed K6 into concentration of CH3O into concentration of M. Similarly, in the seventh reaction, plus K7 into concentration of CH3 into concentration of O. This is the steady state applied on the concentration determination of free radical DH. Now similarly we can write equation for d by dt of O. In second reaction oxygen is forming, so it is K2 CH concentration into concentration of H into concentration of O2. In the third it is consumed, so rate is equal to this minus K3 into CH4 into oxygen concentration. Comes to 5 reaction. In the fifth reaction it is being formed, so it is with plus sign plus K5 into concentration of CH3 into concentration of O2, and the seventh it is also decomposed, so it is equal to minus K7 CH3 concentration into O concentration. Next equation is for d by dt of OH. Steady state concept applied to the concentration of OH free radical. It comes out to be in second reaction K2 concentration of H concentration of O2 plus K3 concentration of CH4 into concentration of O, because in this case OH is being formed, minus K4 it is consumed, so it is equal to K4 OH into CH4 concentration. Now we come to d by dt of CH3. CH3 is being formed in the reaction second, fourth, fifth, second and fourth. So rate is equal to, in first also, K1 into concentration of CH4 into concentration of M plus K3 into concentration of CH4 into concentration of O plus K4 into concentration of OH into concentration of CH4 minus K5 into concentration of CH3 into concentration of oxygen minus K7 into concentration of CH3 into concentration of O. Simplifying these equations, and the equation in terms of CH3 is obtained as follows. d by dt of CH3, d by dt of CH3 is equal to 4 Ki CH4 concentration into M concentration plus 5 into K5 CH3 concentration into OH2 concentration. If CH4 concentration, M concentration and oxygen concentration are constant, this expression on integrations yield the equation CH3 SS is equal to K1CH4M upon K5 oxygen concentration in the bracket E raised to power 4 into K4 concentration of oxygen into T minus 1 bracket close plus CH3 concentration bracket में exponential e raised to power 4 K5 into O2 concentration minus 1. The equation in forms of CH4 is d by dt of CH4 is equal to minus 4K1 CH4 into M minus 5K5 CH3 into concentration of oxygen. This is equation number 2. Substituting values of CH3SS in equation 2 and assuming CH3 concentration into is equal to 0, and on rearrangement we get equation as d by dt of CH4 is equal to minus K1 CH4M in bracket 5 into e raised to power 4 K5 concentration of oxygen raised to power T minus 1, which on integration yields the equation CH4 concentration of O minus CH4 concentration is equal to minus 1 exponential 5K1M upon 4K5 oxygen into 1 minus e raised to power minus K4 raised to power e raised to power minus 4K5 O2 plus 4 upon 5 K5 O2 into H. The induction period or inductions time Ti, the time during which 10% or the methane is consumed, it is obtained that Ti is equal to 1 upon 4 K5 concentration of O2 ln 0.08 K5 oxygen upon K1M plus 45 4 K5 concentration of oxygen into T. This is equation can be solved by the method of interaction interactions. So students, here we have completed the low temperature oxidation of methane. Thank you so much.